Hello everyone. This is a tutorial and experimental video of FTIR spectroscopy. Spectroscopy is where the spectrum of light source is analyzed through a spectroscope to determine the atomic composition of a substance or a sample which is unknown to us. Fourier transfer infrared spectroscopy, also called as FTIR, is a technique that used to obtain an infrared spectrum of absorption or emission of solid, liquid, or gaseous sample. So, FTIR basically uses a beam that contains many frequencies of light at once and measure how much of that beam is absorbed by the sample. The frequency at which a particular molecular bonds absorbs infrared radiation will be different over a range of bonds and modes of vibration depending on the atomic size, the bond length, and the bond strength. The basic principle here is when a material is irradiated with infrared radiation, absorbed IR radiation usually excites molecule to a vibrational state of higher energy. The wavelength of light observed by a particular molecule is a function of the energy difference between the at rest and the excited vibrational state. The wavelengths that are absorbed by the sample are hence characteristics of its molecular structure, and therefore FTIR is a commonly and very crucial technique for molecular study. So if we look at the frequency at which a particular molecular bond absorbs infrared, then yes, it is depending upon the atomic size, the bond length, and the bond strength. So there are basically the two types of vibrational changes which are being observed, which are being captured. One is the bending vibration, and the other is the stretching vibration. So if you look the stretching vibration, there are two types of stretching vibration. If you see in this figure, there's a symmetric stretching. If you can just follow this arrow, you can understand what this vibration means. So there's one symmetric stretching and the other is asymmetric stretching. Similarly, there's another vibrational changes of bending, or also called as deformation, which are categorized as vibration of scissoring, twisting, wagging, rocking. So these are the two type of vibrational changes that are commonly being captured. Commercially available available spectrometers, they usually use the Michelson interferometer, which are having a variety of scanning mechanism to generate the path difference. So in a typical Michelson interferometer, which is being represented here, so this is commonly adapted for FTIR, and here the light from the polychromatic infrared source is collimated and is directed to a beam splitter. Here, nearly 50% of the light is refracted towards the fixed mirror, and 50% of the light is transmitted towards the moving mirror. Now, light light is basically reflected from the two mirrors and then back to the beam splitter. Here, some fraction of the original light passes into the sample compartment, on which the light and this light is basically used to focus on the sample. Once the light is leaving the sample compartment, this light is refocused again on the detector. So, if we try to look at how does the FTIR spectroscopy provides its result, so the typical FTIR spectra is, for example, this is represented here for any material, including solid, liquid, or gas, is presented as plots of intensity versus wave number. So, wave number is the reciprocal of the wavelength. The intensity can be plotted as the percentage of light transmittance or absorbance at each wave number, or we can just normalize the transmittance into transmittance index as represented here. the to recognize the new material or or your sample, the unknown IR spectra or IR absorption spectra is usually compared with the standard spectra of a known material. So the match of the spectra helps in the identification of the constituent which are present in the sample. If we see that there's a band range from nearly from 4,000 to 1,500. Now these are typically due to the functional group like OH, C double bond O, NH, CH3. If you can see, I have marked few of these peaks over here, and what functional groups they are representing. However, if you look at the region between 1500 to 400, these are the fingerprint region. The reason behind this is that the absorption band in this region are generally due to the intramolecular phenomenon, and this phenomenon is usually very specific to each material. So this is how you get information about you get molecular information of an unknown sample by comparing it with a known or comparing with a standard sample whose spectra is known. Let's now move to the experimental demonstration part of FTIR, and this will help for better understanding of the experimental performance and the concepts which we discussed currently. This is the demonstration video of FTIR. The FTIR which is placed right front of you is the ATR FTIR from Bruker. Uh, as I already discussed most of the principle in the tutorial video, let's now look at the instrumentation part. The majorly the instrument consists of an ATR crystal, which is placed here. Now this ATR crystal in this system is made up of zinc selenide. It has a this ATR crystal This ATR crystal is designed in such a way that it should have a high refractive index than the sample. During the sampling, the sample is placed at the ATR crystal so that there occurs the maximum contact between the sample and the ATR crystal, and the IR light that comes from the downward passes through the crystals and get reflected internally, and then finally get absorbed by the surface of the sample. There are few things that we have to take care about is, for example, we are using a solid sample. In that case, we put a tiny amount of sample on the ATR crystal, and we try to put a force with this probe so that there occurs a maximum contact between the sample and the ATR crystal. However, for liquid crystal, and at the same time it is used to fill any kind of air bubble or any kind of gap that may occur during the sampling process. However, during the liquid sampling, we just place the tiny amount of sample and continue reading it in the software which is provided. Let's now move to the software and let's learn how, and let's look how this particular instrument is handled through the software. There's one thing that always we take care of is the sample, especially the liquid sample that we are putting for sampling. The pH of them should always range from 5 to 8. Let's now load this sample. We'll take it. So the sample which we are using is an oleogel sample. This is a sample which is having some semi-solid texture. So we'll take a tiny amount of sample with a spatula, and we'll put it at the ATR crystal, and we'll just firmly press the sample so that it makes maximum contact with the ATR crystal. And we'll do the further analysis in the software. Let's now look how the FTIR analysis takes place, or how do we do this measurement through the software.
So before starting, this is how the window looks like, and we'll click on the button which is shown as measure, and we'll click the setup measurement tool, and here we'll put the advanced option. Now this this window includes the information about how do you where you want to save your file. So we'll just set a desired location, and then there are few important information, for example resolution, sample scan time, background scan time. So these are, and then the data from or the range of spectrum which you want. Here we have set it as a complete spectrum. We'll click, the result can be given in the form of absorbance, transmittance, reflectance, based upon how do you want to put your data, and we'll just click on atmospheric compensation over here. So if you see in the window, there are the sample scan time basically means that for how many number of times the sample will undergo the scan. And since I haven't provided the path initially, I'll provide the path now. I'll just make a new folder, and then we can just click on accept and exit. Once this is done, all we have to do is now is a background compensation. So once we have already set the measurement parameters, we'll click on the measurement, and we'll now run the background measurement. So we'll just click on the start background measurement over here, and then it will start. So if you can see downwards, there are the number of scans are shown. So right now there are 5 scans. So as we have set it for 24 scan, the system will do the 24 scans for the background measurement. So once this is done, once the background measurement is done, we'll just now, so once the background measurement is done, we'll just put on the sample name. We'll start with our sample measurement. We'll put, for simply, we'll put sample name as S1, and we'll start the sample measurement. So I have already said, we have set the parameters to 24 scan. So once the 24 scan is done, the we will find the we'll get the obtained spectrum of the sample in the range from 600 centimeter inverse to 4000 centimeter inverse. So this is the absorbance spectrum which is obtained. So if you look clear, if you can recollect from our tutorial video, the spectrum is same. The only difference is the one which I have shown you is for transmittance. However, this is for the absorbance spectrum. So here each and every individual peak basically represents something. For example, a peak over here around 3007, this represents, for this basically a representation of a ch stretching. However, this peak is for the ch stretching bond, or the vibrational bond of ch stretching. The next peak represents the ch stretching in alkanes. However, the smaller one is for the alkenes. So these are the thing that we get it from the literature. If you look clearly, the sharp peak here at around 1742, this is for the C double bond O stretching, or for the, which is basically obtained from the ester groups. And this one at 1746, yes. So if we'll move forward, we'll see that there are peaks which are for single bond O stretching, which is around 1159, and this is for the, as I said, it is for the C double bond O stretching of Easter, and that one is C single bond O stretching vibrational energy. So here it is very clear, and ultimately we have a last peak at here around 720. This is for the CH stretching of alkene. So as I said, the each and every peak which we get from either the absorbance or the transmittance peak, it is being represented for some kind of vibrational energy, either the bending or the stretching, as we have already discussed in our tutorial video. So these are.
As you have already seen how to take the FTIR data with this machine. So now what we will do is that we will take two samples, one is salicylic acid and one is sodium salicylate, and we will perform the FTIR analysis. And the work of you guys are that I will provide you the data, FTIR data. You have to analyze the data. Now we will load the sample. So you can see how the sample is loaded here. Now the sample is loaded. Now let's see. Now go to the software part. As you can see that the process is already initiated, so it will take some time. So this is the FTIR of salicylic acid. Now we will see for the sodium salicylate. So we have loaded the sodium salicylate here. Now we will perform the analysis. So the process is initiated. Let's see, wait for some time. So this is the FTIR of sodium salicylate. So this is all about today's lab. So thank you.